Hello guys, welcome to MedZs where education meets excellence. And today we will be talking about why the proximal convoluted tubule is one of the most important component of the nephron. But before we do that, we'll have a look at this question. We have here a nephron with its parts labeled A, B, C, D, and E. And the statement reads as which part of the nephron normally reabsorbs the most amount of water? Is it A, B, C, D, or E? The answer is A, and this is the proximal convoluted tubule. So the main objective of this video is to help you understand the ultrastructure of the PCT, understand the functions of the early and late parts of the PCT, understand how substances are reabsorbed and secreted in the PCT, and understand and comprehend in the end why the PCT is the most important component of the nephron. So the proximal convoluted tubule is actually the longest part of the nephron, with each of its cells around 10 micrometer in length. These are actually cuboidal epithelial cells, as you can see here, and they're actually joined together by each other by tight junctions. So imagine there's a proximal convoluted tubule cell here, and there are going to be a lot of tight junctions here. Important thing to note is that these junctions are not watertight, which means water can easily pass through and fro depending upon the concentration of the solvent. So this side of the membrane is the luminal side of the membrane. It actually lines the lumen, and it is highly specialized in the fact that it has a lot of brush borders and microvilli specifically, and these increase the surface area for reabsorption and secretion. And this here, as you can see here, is the basolateral membrane, and this lines the renal interstitium and is in contact with the peritubular capillaries. A distinct feature about the basolateral membrane is that it is lined a lot by these mitochondria, as you can see here. So we can imagine that there is something in the basolateral membrane that's using up a lot of ATP because a lot of mitochondria have lined here. And what is that, you may ask? That is the sodium-potassium ATPases. So having a look at the ultrastructure of the PCT, we see that the main pumps present in the basolateral membrane, as you can see here, is the sodium-potassium ATPase, as I mentioned before. These are the main pumps of the proximal convoluted tubule and drive most of the reabsorptive purposes of the PCT. And they're present specifically on the basolateral membrane and not on the luminal membrane. Another pump that is present is the sodium bicarbonate pump, a co-transporter basically, and this pump is usually involved in the acid-base balance of the cell. The luminal side of the membrane, there are a lot of these co-transporters which actually pump sodium along with substances such as glucose, amino acid, chloride from the tubular lumen and into the cell and eventually back into the blood. Also present on the luminal side of the membrane are these sodium hydrogen antiporters. These are once again important in the acid-base balance. They take in sodium and pump out hydrogen ions. An important thing to note is that substances absorbed along the PCT or along the PCT length are not actually the same. What do I mean by that is that we see that the early part of the proximal convoluted tubule is mainly involved in the absorption of glucose and amino acids. 100% of the glucose and amino acids are basically reabsorbed here. So if we have a clinical scenario in which glucose or amino acids appear in the urine, we have we highly suspect that there's something wrong in the proximal convoluted tubule. 65% of the sodium is also reabsorbed. And whenever sodium is reabsorbed, it creates this high concentration inside the cell, which in turn pulls water in by osmosis. So there is an isosmotic absorption of water. 90% of the bicarbonates are also reabsorbed, along with some phosphates, and urea also passively diffuses. Some divalent ions such as calcium and magnesium are also reabsorbed. But talking about the late part of the PCT, it is highly specialized for absorption of chloride ions. Basically, due to the presence of sodium chloride co-transporters, a lot of chloride is reabsorbed in the late part of the PCT. If you talk specifically, it's 50% of the chloride ion. So to understand how the early and the late parts of the PCT work, It is important to recall the concepts of diffusion and osmosis. Initially, the sodium-potassium pump present on the basolateral membrane uses energy in the form of ATP directly and pumps out sodium out of the cell and potassium into the cell. This creates this decreased concentration of sodium inside the cell, and this process is known as primary active transport. Consequently, sodium tries to move from an area of high concentration in the lumen to an area of low concentration inside the cell. But it just can't do that simply because it's a charged ion, and charged ions cannot pass the cell membrane. So sodium is moved into the cell with the help of these co-transporters. And it carries along with it a lot of glucose and amino acids, depending upon the pump. So we see that the movement of glucose into the cell is actually by active transport, as it is sucked up against its concentration gradient because of the co-transporters. The movement of glucose is independent of the concentration inside the PCT, as we can see. So this active uptake of glucose that happens due to the passive movement of sodium into the cell is called secondary active transport. Or if I rephrase my statement, I would say as this passive movement of sodium from the lumen into the cell due to the concentration gradient created by the sodium-potassium ATPase by primary active transport causes the glucose to be taken up against its concentration gradient, and this is the phenomenon of secondary active transport. This is chiefly how the PCT actually reabsorbs 100% of the glucose and amino acids. So yes, this is the same case for these hydrogen ions, but instead of being reabsorbed like the glucose and the amino acid, they're actually pumped outside by these antiporters I mentioned before. So the late PCT works primarily in the same way as the early PCT, but the late PCT is specialized for the secondary active uptake of chloride ions. So the overall picture is that due to the excessive amount of solutes that are pumped in by these co-transporters, the concentration inside the cell becomes high. This, as a result, tends to move the water in from the lumen into the cell by a process called osmosis. So we can see that 65% of the sodium that is reabsorbed causes 65% of the water to also be reabsorbed. So the overall concentration inside the lumen actually remains the same, which is quite surprising actually. As so much solutes are reabsorbed, a person may think that the concentration may change, but no. The reason is because the leaky channels and actually the cell membrane itself allow the movement of water by osmosis. So the concentration gradient that is created causes the water to move in. And this is the phenomenon of isosmotic absorption. But what does actually change is the volume of the solution in the lumen. Why is that? Because a lot of water and a lot of solutes are actually reabsorbed, which causes the volume in the lumen to decrease. One of the most important functions of the PCT is actually secretion. These are the substances that are actually secreted by the PCT, and one of the most important ones is hydrogen ions. The PCT actually secretes a lot of hydrogen ions and prevents acidosis to develop in the body. Other substances such as end products of metabolism such as creatine are also actually secreted by the PCT, and creatine specifically is almost 100% secreted. Organic acids and bases are also needed to be secreted because they can damage the cells. Bile salts, oxalates, urates, and catecholamines need to be secreted because they can actually damage the body in excess amounts. An important role of the PCT with its role with pharmacology is the secretion of drugs, mainly penicillins and salicylides. And anti-gout drugs such as probenecid can actually act on the PCT and actually prevent the secretion of penicillin and salicylides. And this can result in the prolonged actions of these penicillins and salicylides, which we do not want to see. Other substances that are secreted are actually toxins, which can damage the body. A synthetic molecule such as para-aminohippuric acid, which is actually 90% secreted by the PCT. This is important in some renal functional tests which we'll look later on. So here in this slide, I have put the concentrations of certain solutes along the length of the PCT. And to sum it all up, we can see that the concentration of waste products such as creatinine and urea and the waste, which are the waste products of metabolism, actually increase because they are secreted into the tubular lumen. But the concentration of sodium chloride actually remain the same. Why is that? It is because they are reabsorbed isosmotically. Water also follows with them. Bicarbonate is also reabsorbed, that is why its concentration decreases. And amino acids and glucose actually become 100% reabsorbed, so their concentration in the lumen actually falls to 0%. So the creatinine and urea are actually secreted, so thus their concentration is increased. Sodium chloride are actually isosmotically reabsorbed. Bicarbonate is actually reabsorbed, that is why its concentration is decreased in the lumen, whereas amino acids and glucose are actually 100% reabsorbed, so there is no quantity present in the PCT after it is done with it. So that's all for today, folks. Hope you had fun learning with us. If you did, make sure you give us a like rating and share the video with your friends. Do let us know if this video helped in the comments below as well. Till next time, Allah Hafiz.